And we are going to be concluding our aquatic species talk. And to wrap it all up for us, we have Aubrey Harris from the U.S. Army Corps of Engineers. And today she will be presenting engineering modeling applications for quantifying habitat for the Rio Grande Silvery Minnow.
Good morning, everybody. Thank you guys very much. It's been a great symposium. I really appreciate hearing from the scientists about their monitoring efforts and the data collecting. And I want to talk about applying engineering tools for learning more about the hypotheses that are being presented and some of the both hydrologic and hydraulic challenges. Previous 4 years, I've been working with the Bureau of Reclamation. And so working with Jennifer Bacchus and Aaron Gonzalez and doing literature review regarding the silvery minnow habitat. Going to be just focusing on the area that there's been a lot of research and interest in, including the rearing habitat as a case study for my modeling presentations. And also talk about as we develop and become more certain about our conceptual models as we walk towards applications, looking back on what we've learned in the conceptual models and how they could possibly apply to engineering modeling outputs. I'm going to present 2 HEC models that are available. And they're great because they're free to the public. The HEC ecological function model developed by John Hickey, and then the river analysis system, especially the 2D model functionality. But starting with some of the most fundamental, what are we doing? A lot of our presentations, I see that we're talking about the system, the real system. What are we observing as far as ideal habitat for whatever species that of interest, and trying to make inferences about, well, what conditions are creating this ideal habitat situation. So we hear a lot about the floodplain coming up in these most recent talks. And what about the floodplain? Is it the fact that you have a roughness that's slowing down velocities, or that the water is spreading to lower depths? And those are inferences and hypotheses that we can continue to understand more about, going beyond, say, our monitoring sites when we're there for one period of time, to being able to model situations throughout the hydrograph. And what's necessary for modeling is parameterizing. So when we're talking about depths, velocities, shear forces, those are parameters. We say that there's like a range of values that are appropriate for the habitat that we're interested in observing. And so what I'm really, or what we do as hydraulic engineers and hydrologists, is representing the system with a model. And as I say, it's a benefit to do the model and represent the system because you're only able to gather data so frequently. And so that presents an opportunity to gather information for in between those monitoring times. What I appreciate about Bovie is that he presents that there is opportunity for error. We can make improper conclusions and valid conclusions. And so the incremental checking back, being willing to recheck our assumptions is critical. And this all feeds into, or modeling feeds well into the adaptive management framework, in that we're trying to move away from just doing a trial and error, but to be able to anticipate what possible changes we may come up with, and coming up with solutions in anticipation with potential changes. And I just want to give some examples, and we've been talking about them all throughout this conference, about all these different ways that we are really parameterizing and describing the silvery minnow environment. And the hydraulics and hydrology modeling really feeds well into information in that you can get better understanding about the frequency, magnitude, and the duration of your events. as the conceptual models bring in the life history of the Silvery Minnow, being aware of how the hydrology throughout the year varies, and also kind of what scale is always a question with modeling, at least with the benefit of modeling data is that you can have a lot of information, but what is the critical information and what are these system-wide trends that are affecting the longevity of, say, your habitat restoration projects. And I have imagery of 1918 and 2016 thinking about 2000 CFS running through the river 100 years ago. It certainly has different hydraulics compared to now. So I'll go into the ecological function model. As I said, these are free and open to the public. So as you're testing your hypothesis, what this is developed, it's a statistics. So you can input your USGS data for any gauge for any time period to inspect, say, in this example, we're inspecting, say, the rearing habitat that is generated in the Albuquerque gauge area. And so you want to pair it with hydraulic modeling so you can get data about, okay, how is the water actually laying on the land? When do your bank full flows exceed and start going into the floodplain in those areas? But for this section, you can define your season. So what days of the month. And so if you were just looking for the peak, you don't have to go through every single year. You can just target on those years or those months of interest, those days of interest, what type of duration event. There's discussion about whether it's a 14-day runoff or the 28-day, 35-day runoff that is of interest. Computing, say, the maximum. So this would give you a peak, but I'll give you other examples of how to parse up, say, the spring hydrograph. And then also your percent exceedance, like how frequent are these events occurring? If you know that your species, say, lives for longer than a year, or you're concerned more about mortality over several years or the spring runoff multitude effects, you have the opportunity to do that. What's also, I think, has a lot of opportunity in this tool is that you can test hypothesis. So if you have a relationship between your discharges and say if you are concerned about a rate of recession or your area of a certain velocity or depth, then you can track and compare what it's pulling out for each year to generating an eco value for that year. And the meaning of the eco value will really have to depend on how you interpret the data or what inputs you have. And so just as an example, this is the Albuquerque gauge with the eco value just associated with the maximum of that spring runoff event. And so if you have fish data or annual monitoring data that you're interested in reviewing, you can also test your hypothesis of how strong does your population's data actually match with what you're saying is influencing the population. But this is challenging. There's many ways to parse the spring runoff. As stated by Jake, it changes every year. And it's important to reflect on that, what kind of data you're pulling out from your spring hydrograph. And here's just an example of how many different values you could get for parsing out that spring runoff event from the maximum and maximums, the maximum minimum of the 14-day runoff. So what's your minimum runoff discharged during that 14-day peak? The means, there's a lot of information, and certainly you can model all of them, but we do want to get like kind of stronger understanding of what factors about the hydrology are influencing or are more correlated with populations and habitat effectiveness. So for the river analysis system, it's really a good time for two-dimensional modeling. We're routinely collecting data at a resolution to create terrains. And also, as you are collecting monitoring sites, If you're going out to the field and collecting velocities and depths at particular points, you are gathering information that can inform 2D modeling. An advantage of 2D modeling over 1D is that it's more effective at modeling areas of habitat interest, including the side channels and then bayments, channel edges, areas where flow is complex. And with pairing this with civil 3D capabilities of being able to build terrains of your habitat restoration sites, you can do alternatives analysis ahead to understand how the hydraulics are going to be occurring in your site. And it's quantitative, so if you're able to map your area of interest or areas beyond, say, where you're collecting monitoring data, you can gather some quantitative information for comparison. And I just wanted to give some of the examples of results that we've generated over, particularly at my time at Reclamation, working on the Bosque del Apache project. There were concerns about conveyance, water conveyance, so we were doing two-dimensional modeling to demonstrate when there's a flood event, is the water going to be pooling in that area or not? But we also took the advantage of the fact that we had a 2D model and we're defining some habitat criteria from the literature that you could map relative areas of how much areas you're actually meeting your ideal velocity and depth criteria, and getting a quantity, also getting an idea of areas of opportunity for restoration or mitigation from the vegetation removal. Also, comparing sites over time, if you're collecting monitoring data and building the model continuously, you can just see how effective your site is at meeting your goals of if your hypothesis is that a certain duration of inundation is occurring, if you're creating particular habitat like from the hydraulics, you can map compare over time or for species life stages. And another example is just duration, say, through a long time period. And so we're really excited about this. I know that H&H at the U.S. Army Corps of Engineers, we're really trying to develop our ecosystem hydraulics abilities, because there's definitely concerns with various different species. There's opportunities in the middle Rio Grande, just as with its special sediment and hydrologic characteristics. But if you are interested in learning more about our projects, here are various project managers that I'm working with currently. And again, thank you very much for the invitation to this presentation.
Thanks, Aubrey. Just a question, thinking conceptually about specifically the 2D gas modeling. I've mostly spent a lot of my time in the field, and as a person in the field, what can we provide you and other modelers using these products? Field data is best, what do you need most, I guess?
And it's certainly a challenge. I think engineers tend to be very quantitative. And I think just talking about being able to describe what good habitat looks like, or if you're observing certain substrate being left on the site, just describing the environment in ways that can maybe be translated into being able to interpret these sites. But as I said, being able to gather topography, your depths and your velocities is very helpful for calibrating these models because they are sensitive. Roughness is pretty much our black box of what we're saying, like affecting the water surface elevation. But I would say that it requires an iterative approach because every site is different and we're constantly learning new things for each of these sites. And I'm just hoping that these tools can help us anticipate that.
Aubrey, I have a follow-on question to that. I'm thinking about, as a follow-on question, I'm thinking about what John Peterson presented yesterday about using the collector app. And so could we send people out to get data that would be relevant using that? Like, get the roughness, what's going on in the floodplain. It doesn't even have to be inundated. You can go out when there isn't water there and say, here are things that might be contributing to roughness or some other attribute. Would that be helpful?
I think photographs are very helpful, and what's helpful about being able to do the modeling is say that you model a spring runoff event. There may be areas that you were biased in thinking that we're not going to be inundated, and that could signal a location that may be of interest. Or if you're calibrating, looking into an area thinking that you would have inundation and going out in the field and realizing that there's not. The model's only going to be as useful as it represents the real system, but also the areas of interest.